Welcome back. Today we're going to talk about the washer method. It's a lot like the disk method, except for, well, as you'll see, we'll end up with washers instead of disks. Picture, if you will, this box, which you can see, so it's not that hard for you to picture. What we're going to do is we're going to take this region right here, and we're going to rotate it about the x-axis. So picture as we come out of the x-axis, it's going to come into the screen about here, and then it's going to go back out and come around and create a three-dimensional object. What sort of three-dimensional object? Well, see this little picture over here, and whatnot. We're going to get a washer. Picture the washer, and just make it just a touch bigger so you can really see that square piece comes out, goes back in, comes around. So we get a washer. With the washer, it's a couple things we need to take care of, keep track of. That what we have is we have a large radius on the outside, and then we have a smaller radius on the inside. Okay? So with this washer, the outer radius is this big R, and then my inner radius is the little r. In terms of the process, it's very much like what we did yesterday with the, oops, get it this time. Very much like what we did yesterday with the disk, except for instead of just doing the area of a solid surface squared, pi times the radius squared, we've got to subtract away the area of the whole part. So what I talk about is that this gives me the area of the whole thing, and then this part gives me the area of the whole. So typically we're just going to do the whole minus the whole. And it is important that it's pi big R squared minus little r squared. We don't want to do the subtraction and then square it. That gets us a different shaped object. Okay? So that's the basic idea. We're going to still, if we're going to get to something larger, we're going to find out the area of first the area of one of my washers, multiply it by thickness to get the individual washer, and then depending on how long it is, we're going to just stack up a bunch of these washers together. That's what the integration part does. Okay? So let's try one, shall we? So we're going to try to find the volume of the solid generated when the region defined by, you can read it, y equals the square root of x, which is this curve, and y equals x squared, which is this curve, is revolved about the x-axis. Okay? Picturing what that looks like, the best thing that I can describe, and I probably should have found some sort of graphic, but when I tell you what it is, you'll wonder why, but you can try to find one later. This part on the outside makes the gumdrop. The inside, kind of like a funnel. So we end up with a gumdrop where we've somehow jammed a funnel into it. That would have been a good graphic to get. So we get some sort of a hollow sort of gumdrop, but the inside of the gumdrop has got like a funnel-y sort of shape to it. All right. So as we're working our way through this part is going to be my big radius. This part is going to be my little radius. So, if this part wasn't here, we'd get a big solid gumdrop, and then we're going to subtract out the funnel-y portion of it. So the formula is that for the volume, we're going to do pi integral of big R, which is the y equals the square root of x, that's big R, and the little r is y equals x squared. So big R squared minus little r squared dx. Again, this is the whole, and this is the whole. Okay, so the whole minus the whole gives us the actual volume that we're looking for. Where are we going to integrate from? Well, we need to take a quick look and see where these two functions are equal to each other. When is the square root of x equal to x squared? They're going to be equal to each other. Well, if we square both sides, we get when x is equal to x to the fourth, and that happens when x equals 0 and when x equals 1. Turns out to be plus minus 1, but we're not worried about that portion of the curve. So we're just going to integrate this thing from 0 to 1. Simple enough. Let's go a little further with this one. Maybe we can even do this whole one out. We haven't done a whole lot of these lately. Square root of x squared is just x. X to the squared is x to the fourth. dx, integrate. We end up with x squared minus, how about x squared over 2 even, x to the fifth over 5. We're going to evaluate that 1 and 0, and no, I did not forget the pi. It's right there. Say nicely enough, the 0 is going to disappear. No, not disappear, just not going to count. 0 squared plus minus 0 to the 5th, it's all 0. So we're just going to end up with pi times 1 squared over 2 minus 1 to the 5th over 5. That's a 5, believe it or not. As it turns out, it's a half minus a 5th. So we need the old common denominator trick. This would be 5/10 probably, minus 2/10. And so we end up with 5 minus 2, 3/10. So we end up with 3/10 pi, okay, as the volume of the region that we get when we spin this odd-looking shape around here. That's the this is the volume of our little gumdrop with the funnel taken out of the middle of it. Okay, so on to the next one. Well, the next one, it looks an awful lot like the first one, except for in this case we're taking the same region and now we're going to rotate it about this line right here. It's the first time we've done anything where we haven't rotated about one of the axes. It doesn't make that much difference. We've still got to identify my big radius. Okay, notice my big radius now is relative to the axis of rotation, and my little radius is right there. Okay, so the question is, how far is it? You know, what is my big radius? My big radius is this distance plus that distance. So it ends up that my big radius, capital R, is 2 plus the square root of x. My little radius is 2 plus x squared. Okay, once again, it's x squared from here to there, plus this distance here in between is 2. Okay, if that's 2, then, and this used to be little r, so it works out to be that. Integral is going to be the same thing as we go. This one, I don't know what it actually looks like, but we'll have to try to figure that out, what it turns into. You can try to visualize it if you like. My volume, still pi integral, still from 0 to 1. We haven't changed the points of intersection haven't changed anything about this curve. Big R, 2 plus root x squared minus little r, 2 plus x squared dx. Okay, so we could do this one. Again, we'd have to do the expansion out, combine like terms. I probably would run to the calculator. You all know how to do that. Plug this in and get yourself an answer. So we're not going to belabor the point of actually getting an answer because you've got the calculator do the work. We did one already the other way. Okay, so process not any different. We've just got to keep track of where we're rotating about when we're rotating about some other point other than just one of the axes. All right, last problem.